Today we'll be discussing quiz chapter 10 section 1 and 2. So quiz C10S12. So there are around 7 or 6 questions to discuss here. So let's start with the first question. So this is question 4 from the quiz. It says that what is the phase difference? So the difference between two different phase, the phase difference between 2 points separated by a distance of 3 cm. And this is in the wave of wavelength 5 cm. So what does it mean is if you have a wave of 5 cm and you are interested to find what is the phase difference between two different points that are separated by 3 cm. Okay, so let's try to draw out the situation maybe. So we know that a wave looks something like this. So let's draw a sinusoidal wave. So this is what a sinusoidal wave looks like. So over here, I have drawn two complete wave cycle. So as you can see here, this is the first wave cycle and the second wave cycle over here. Okay, so when we say what we are finding here, it's phase difference, right? Phase difference is represented by the symbol delta phi. So this is the difference. This is the phase. That's why I call it phase difference. So technically, the way to do it is take the final phase minus the initial phase. Okay, so the idea of phase is you need to know that one complete wave cycle is equivalent to 2 pi radian. So this is in terms of length. This is in terms of phase. Okay, instead of saying length, probably the better word is distance. In terms of distance, if you complete one complete wave cycle, then in terms of phase, you have completed 2 pi worth of radian. So let's say it can start from anywhere, okay? So let me give an example. Let's say if I start from here, then this point here will be where we start. So this will be initial equals to 0. So if you complete one wave cycle, then you reach here. So that means this point over here, the final phase will be 2 pi. Okay, because in terms of length, you have finished one complete wave cycle. So what we have here is one wavelength. But in terms of phase, we have completed about 2 pi worth of radian. Okay, as you can see here, you can take final minus initial. So if you take final minus initial here, then it's 2 pi minus 0. So the phase difference will be 2 pi. So this phase difference is the phase difference between this point and this point over here. Okay, but that's not what the question asked for. So let's try to clear things up and try to do what the question asked for. Okay, so now we know this is the situation that we have here. So let's don't call this final, don't call this initial. Okay. So this is 0 in terms of phase. This is 2 pi in terms of phase. Now they are not interested with this 2 point over here. We know that the lambda is 5 cm. But they're not interested in these 2 points that are separated by 5 cm. They're interested with the 2 points that are separated by a distance of 3 cm. So if they're interested with this, then we have to find where is 3 cm. So I believe 3 cm it's around here, maybe somewhere around here. Okay, so they are interested with this point over here. So in terms of distance, the distance between these 2 points over here will be 3 cm. But in terms of phase, how much is the phase difference? This is what the question asking about. This one, phase difference equals to how much? Okay, so the idea that we will be using right now is we'll be doing a ratio actually. We know that if you complete an oscillation, you undergo a phase difference of 2 pi. This is one complete wave cycle. If it's one complete wave cycle, you complete 2 pi, and in terms of distance, you complete 5 cm worth of distance. Okay, this is one complete wave cycle. So now if you're interested with the 2 points separated by 3 cm, then you know that the distance between these 2 points, when we say distance, we are not saying the distance from here to here, we are saying the distance in terms of x. Distance from here to here, we know that the distance will be 3 cm. And now the question is, what is the phase difference? So this is how we build the ratio. We know that for one complete cycle, in terms of distance, we have traveled for 5 cm. In terms of phase, we complete one complete wave cycle, that's why it's 2 pi. But if we look at these 2 points that are separated by 3 cm, we know the distance between them is 3 cm. So now we can try to deduce what is the phase difference from here to here. So we are building a ratio. So this left hand side is for one complete cycle. This right hand side of the ratio is for 2 points separated by 3 cm. So now if you reshuffle your equation, putting delta phi, the phase difference on the left hand side, then what you get is just 3 divided by 5 times 2 pi. Okay, so from here we know that our answer is this one. 3 divided by 5 times 2 pi will be the phase difference between these 2 points over here. Okay, so when you face this kind of situation, just build a ratio. For the left hand side, you can use one complete wave cycle. For the right hand side will be the one that you are interested in. Okay, in this case, what we're interested in is the 2 points separated by 3 cm. Okay, so now let's move on to the next question. So the diagram above shows the position of the particles. So these black dots here are particles in the medium. So let's say this is air molecule. So these are a few air molecules that we are interested in at a particular instant. Okay, so this is the position at a specific moment when a sound wave of frequency of 1500 hertz pass through it. So you know that there's a sound wave of 1500 hertz passing through this medium here, and at this particular moment, if you take a snapshot, this is what we can see for the particles at that specific moment. And now they ask for the speed. Well, if you think about this question, right, you know that they are asking for speed. Speed of sound is just v, and they give you the frequency. Frequency is f. So you know, quite straightforward, you can know that what you need to use is this equation, v equals to f lambda. You have the information here. What you want to find is v. So what you need to know now, what you need to determine now will be the wavelength. So this is what they are testing actually in this question. So let's try to see what is the wavelength for this wave over here. Okay, so I'm going to analyze this wave. This is a longitudinal wave. You might not be familiar how to analyze it. So let's try to analyze it together. So these are the positions of a few particles along the x-axis at a single moment. So you can see that there's compression in this region, there's rarefaction in this region, compression, rarefaction, compression in this region. Okay, so we can see that this at x equals to 5, x equals to 15, x equals to 25, x equals to 35, x equals to 45. At regular interval, there's always a particle over here. So we can actually deduce that these particles here are at equilibrium actually. These particles here are at equilibrium. Then if you see something squeeze over here, that means the particles move from x equals 0 towards this side. If there's particle over here, that means it comes from x equals to 10, move towards that side. So they squeeze towards x equals to 5. Same situation over here. If you look at this particle over here, you know that it comes from x equals to 20, move towards the right. Then this particle here comes from x equals to 30, move towards the left. You can see that they squeeze towards x equals to 25. So all the particles move towards x equal to 5, move away from x equals to 15, move towards x equals to 25, move away from x equals to 35, move towards x equals to 45. Okay, so that's the idea. We need to see what are the particles that are in equilibrium position, and what are the particles that are moving towards where or moving away from where. Okay, so let's do that slowly. So we know that all these particles should be at x equals to 0, x equals to 5, x equals to 10, 15, 20, 25, 30, 35, 40, 45, 50. So that's where the particles originally was. So let's draw the particle as it is. Okay, so what we have here, this is the initial, or you can think of this is the equilibrium position for all the particles. Okay, then when a wave pass through, when a sound wave pass through, then the particle starts to vibrate, right? So this diagram here represents the position of the particles at a particular moment. Okay, so what I'm going to do now is I'm going to investigate whether the particles move to the left or move to the right or remain at its position. If it's moving to the right, we call it a positive displacement or positive y. If the particles move to the left, then we call it a negative displacement or negative y. If the particles remain at its position, we call it remain at its position, so y will be equals to 0. Okay, so let's draw lines. So we draw dotted lines so that we can see clearly whether it moves to the left, to the right. Then if it's moving to the right, like in this case over here, then we plot it above the x-axis. If it's moving towards the left, as in this case over here, then we plot it below the x-axis. And later we'll trace out our graph to see what's the shape of the graph. Okay, so we look over here at x equals to 0, the particles move to the right, so that's a positive displacement. So let's plot it out. It's a positive displacement. Then at x equals to 5, these particles remain at its position, so x will be equals to 0. Next, we can see that the particle at x equals to 10 move towards the left. So move towards the left is a negative displacement, so plot it below the x-axis. Next, we look at x equals to 15. This particle remains in its position, so no displacement, y equals to 0. So continue, we see that this particle at x equals to 20, it displays towards the right, so that's positive displacement up here. Okay, so at x equals to 25, it's at its equilibrium position, doesn't change, no displacement, so y equals to 0. Next, at x equals to 30, you can see that the particle is being displaced to the left, therefore it's a negative displacement. So, oops. Okay, so I will complete the dots. You can check it for yourself. It's the same thing again and again. So if you connect the dots right now, this is what you will see. So this is the graph of displacement against distance for this longitudinal wave over here. So what we have here is displacement y and distance x. So x here represents the position of the particles, then y here represents how much is being displaced either in the positive direction or negative direction. So if you want to determine the wavelength, we can just determine what's the distance between two consecutive points of the same phase. So what you can do is you can take the distance between this point and this point, and you get your wavelength. So I believe the distance here should be, this is 20, this is 0. So we know that our lambda will be equals to 20 cm. Or in meter, it will be equals to 0.20 meter. Okay, you can take any other 2 points, any other 2 consecutive points that are in phase. For example, you can take between this point and this point, you can take between this point and this point, it's up to you. For me, 0 is easy to minus, so 20 minus 0 is 20. So it's 0.20 meter. So now if we substitute it inside here, so we have 1500 hertz for our frequency, and we got 0.20 for our wavelength. So from there, we can determine our speed of sound to be equals to 300 meter per second. So frequency as a unit of per second, hertz is per second, wavelength is meter, so meter per second. So our answer will be this one over here. Okay, so this is how we solve question 5, and this is how we plot a graph for displacement gain distance for a longitudinal wave. Next, so this is question 6. Question 6 says that you have a progressive wave which is represented by the equation above. So the equation is y equals to a sine bt minus cx. So this equation here, it's representing a progressive wave. Now they ask for the speed of the progressive wave. So this should be quite straightforward actually. You know that the equation for progressive wave is always a, it can be sine or cos depending on the initial situation. Then it's always omega t plus minus kx, right? So now if you compare with the equation being given over here, then you may determine that the amplitude is equals to a, the angular frequency is equals to b, and the wave number is equals to either c or negative c. Okay, but we just call it c, don't need to think too much. So from here we know that the amplitude is equals to a, the omega, the angular frequency is equals to b, and the wave number is equals to c. So knowing that already, we can determine our speed of progressive wave straight away. Okay, so usually the equation that you use is v equals to f lambda, but in metrics, right, there's a much more convenient formula which is v equals to omega k, omega divided by k. This equation is much more frequently used because from your equation you usually get omega and k. So this is an easier equation to determine the wave speed. So now we can do our substitution. Omega is b, wave number is c. So our answer is b over c. So the answer should be this one over here. Okay, so if you want to see whether this equation is correct or not, well, you can do omega times 1 over k. Omega is 2 pi frequency. K is 2 pi over lambda. So 1 over k will be lambda divided by 2 pi. So times lambda divided by 2 pi. So you can see that the 2 pi can cross each other out. So you get back f lambda. So v is equals to f lambda. So what I'm trying to show you here is this equation here is valid. Okay, so this is for you to determine the wave speed. Okay, or the speed of propagation of the wave. Okay, so this is how you solve question 6. Let's move on to the next question. So next question is question 8. So you have a progressive wave and it's given as this equation over here, y equals to a sine pt plus qx. So a similar question to question 6 that we have just now. So now they ask which of the following is true. Well, they ask about wave frequency and particle acceleration. Wave frequency, particle acceleration for all options. So you need to determine the wave frequency, which is f, and you need to determine the particle's acceleration. So this will be the equation for the particle acceleration. So we need to determine two things. So let's start from what we did just now. Our first step should be to write out our general equation. Our general equation is A sine omega t plus minus kx. Okay, now you compare with the equation being given in the situation, which is A sine pt plus qx. So from this comparison over here, we can make a conclusion that our angular frequency is equals to p, our wave number is equals to q. So from here we can know omega is equals to p, k is equals to q. Okay, now we know that already. You want to determine, first thing you want to determine is frequency. So that's why first thing you want to determine is frequency. So you know that omega is equals to 2 pi frequency. We have to relate it to the things that we know, which is omega and k. So we know omega is equals to 2 pi frequency. So frequency will be equals to omega divided by 2 pi. Therefore, omega is p. So p divided by 2 pi will be frequency. So if we just look at this option, this first part of the problem, we can already eliminate this one. We can eliminate this one. Oh, we can actually eliminate everything already except for wave frequency. But let's continue. Let's try to determine the particle's acceleration. So if they ask for acceleration, you have to think of each of the particles in the wave there as particles undergoing simple harmonic motion. So if you undergo simple harmonic motion, if you want to determine the equation for acceleration, you take the displacement equation, you differentiate, you get the velocity equation. If you get a velocity equation, you differentiate, you get the acceleration equation. So we know that the displacement equation is y equals to a sine pt plus qx. So if you differentiate it, Vy will be equals to dy over dt. So now this will be d a sine pt plus qx divided by dt. Again, bring out the amplitude because it's a constant. Differentiate sine, you get cos. Write out everything inside. Then differentiate what's inside the bracket, you get p. So what you get is a p cos pt plus qx. Okay, you are differentiating against time. So against time, so you differentiate what's in front of it is p. You treat this one as a constant, so this one you differentiate, you get nothing, 0, because there's no time here. Time is over here, so when you differentiate, you get p over here. Okay, so let's continue. Let's find ay right now. So ay is just differentiating the velocity against time. So now you'll be differentiating ap cos pt plus qx against time. AP you can bring it out because it's a constant. You differentiate cos, you get negative sign. Write out what's inside the bracket. Then you differentiate what's inside the bracket, you get another p. So if you rearrange it, you get negative AP squared sine pt plus qx. So which equation fulfill this condition here? Well, this one. It's just that the a and the p squared, they revert the order. So p squared a sine pt plus qx, yes, it match. Therefore, this one is correct. This one is correct. Therefore, the answer is this one. Okay, so if you see an equation that is in symbols that you are not familiar with, make sure you compare it with the general formula get what is the omega, what is the wave number, what is the amplitude. Then from there, you move forward to determine what they asked for. Okay, so this is how you solve question 8. Let's move on to the next question, question 9. So question 9 asks, the graph above, which is this graph over here, shows the displacement of the particles in a rope. So this is a particles in the rope caused by a traveling wave at a particular time. Okay, so this is the shape of the wave at a particular time. Okay, so the ropes here are made of particles, so these are particles in a rope, and when you're at this particular moment, the particles are arranged like this, which portray the shape of a traveling wave. Okay, now they ask which statement is not true of the motion of the particles in the rope. Okay, so let's bring up. So we know that all along this line over here, this is a displacement position graph or displacement distance graph. Along the line over here, you can think of it as little particles actually. So let me draw it out. You can think of it as many particles. And they are undergoing simple harmonic motion. So this particle here will undergo its own simple harmonic motion. This particle will undergo its own simple harmonic motion. This particle undergo its simple harmonic motion. This particle undergo its own simple harmonic motion as well. Okay, so all the particles on this line, on this rope over here, are undergoing simple harmonic motion. But if you look at it macroscopically, if you look at the rope, this is the shape of the rope right now. So at this position over here, the particle at this position is at its highest point, whereas the particle at x equals 0 is at its equilibrium, the particles at q is at equilibrium, the particle at s is in equilibrium, the particle at r is at its maximum negative displacement. So these are the position of various particles at various position currently at this moment right now. Okay, so they ask for the speed at p, the energy at r, the acceleration at q, and the energy at s. So they are asking about things that we learned about for SHM in chapter 9. So let's try to do a bit of refresh on chapter 9. Okay, so we know here that we have, let's clear all the thing here. We know that we have 4 points, P, Q, R, and S. I know that P and R are at its amplitude, whereas Q and S are at its equilibrium. So what we have here, let's write it down. For point Q and point S, these 2 points here are at y equals 0. Okay, whereas for point P and point R, these 2 points what should I call it? Y is equals to plus minus amplitude. Okay, so we know that the characteristic will differ depending on the position of the displacement of the particles. If the displacement is 0, then it's at equilibrium position, then the speed can be like this, the acceleration can be like that. Okay, if you are at the maximum displacement, whether positive or negative, your speed will be like this, your acceleration will be like that. So we need to recall what we learned from our SHM chapter. Okay, so the 4 things that they're interested in is speed, acceleration, potential energy, and kinetic energy. So let's try to determine these 4 features over here. So we have speed. We have speed is related to kinetic energy. So let's write kinetic energy first. And then you have acceleration. Okay, acceleration is related to net force. Net force is you can think of it as related to potential energy because that spring. If you think about spring, the amount of stretch, the amount of compression that determines your potential energy, right? Then it also determines the force, therefore it determines the acceleration as well. Okay, so let's look at the first one. So the speed, when the speed is at the what is the speed at the equilibrium position? Well, if you're not sure, never mind, but you know that the speed at the amplitude, the speed at the maximum displacement must be equals to 0. C equals 0 because you want to make a U-turn. If you are at the maximum displacement, you want to change direction to go from upward to downward. So change of direction requires you to make a U-turn. So your speed must reach 0 in order to change direction. So if you know that at the maximum displacement, your speed must be equal to 0, then you know that at the equilibrium position, your speed must be maximum. Okay, so next, let's look at kinetic energy. Kinetic energy, it's proportional to v squared. Okay, if your speed increase, then your kinetic energy is increased. If your speed is maximum, then your kinetic energy should be maximum. So of course, if your speed is 0, then your kinetic energy will be 0. Next, let's move on to talk about acceleration. We know that acceleration is very much related to net force. So if you have a greater net force, you have a greater acceleration. We know that net force, if you think about these particles as spring oscillating, then you know that it's related to the amount of stretch or compression. Okay, so stretch and compression, you can think of it like now if you are over here, that means you are being stretched upwards. You can think of it like spring like this. Okay, so now if you are at P, then you are being stretched longer, the spring. If you are at R, your spring is being compressed. If you are at Q or S, then you can imagine your spring is at equilibrium position, not stretched, not compressed. If you are at S, also the same thing, your spring is not stretched, not compressed. At P, stretch. At R, P, Q, R, R at R, compressed. Okay, you can think of it like this. So if you have compression or stretch, then therefore you have a net force. So in this case, the stretch is maximum, the compression is maximum, so the net force will be maximum, the net force will be maximum, the acceleration will be maximum. So acceleration is maximum at P and R. So this place over here, you can see the acceleration is maximum. Then for Q and S, you know that the stretch of the spring, the compression of the spring is 0. Therefore, no stretch, no compression, no net force, no acceleration. 0. Okay, so we know that if the spring is being stretched or compressed, you have elastic potential energy. So the maximum amount of stretch, maximum amount of compression, maximum amount of potential energy. That's going to be max. Of course, if you have no stretch or compression to your spring, your elastic potential energy will be 0. Okay, of course, the principle behind it is not that all the particles are connected to the spring, but you can think of it as HHM. The easiest way of thinking about SHM is thinking about it as spring oscillating. So you can think of the situation as every particle is connected to a spring, which is fixed at one end. Now, when you change height, that means you are changing your stretch or compression of the spring. Okay, so that's the idea. You can think of it like that. The actual mechanism is not exactly like that. Okay, so now we have completed this table over here. We have determined speed, kinetic energy, acceleration, and potential energy at equilibrium position and the maximum displacement. So let's try to check it out. So the speed of the particle at P is maximum. At P, speed is maximum? No, it's 0. So we know that this statement here is wrong. Next, the energy of the particle at R is entirely potential energy. So potential energy at R entirely, yes, maximum potential energy means by 0 kinetic energy. So all the energy are potential energy. So this statement here is correct. Next, acceleration at Q is 0. Acceleration at Q is 0, correct? Energy at S is entirely kinetic energy. So kinetic energy S maximum. Yes, so maximum kinetic energy, that means no potential energy. The energy is indeed entirely kinetic energy. Correct. So now they ask for which statement is not true. So the statement that is not true is the first statement over here. Okay, so that's how you solve this problem systematically. Try to analyze the speed, the kinetic energy, and the acceleration at the potential energy at the equilibrium position and the maximum displacement first, before we move on to see which statement is correct or wrong. Okay, next question. Question 10. Question 10, let's look at the question. Question 10 says that part of the wave propagating in a string to the right at time t equals 0 is as shown in the diagram above. So if we have a string that is propagating a wave towards the right, if you take a snapshot of it at t equals 0, this is what the string will looks like at t equals 0. We know that as time passes, the wave will be moving to the right, as being mentioned in the question over here. Now they say if the period of the wave is t, then which diagram shows the wave pattern of part of the string after period t equals to 4? So if the period of the wave is t, this one we know. For period, we always use the symbol big T, so this statement doesn't give any extra information. The question that they're asking is, what will the wave looks like when t is equals to period divided by 4? When small t is equals to period divided by 4, how will the wave looks like? Okay, so here I have drawn a wave over here. So this part is what being shown in the diagram over here. Okay, this is the part being shown over here. But we know this is only a portion of the string, right? Part of the wave. So this is part of the wave. So you can actually think of it as there's more wave at the left and there's more wave at the right. But this is what being shown in the diagram. So you know that the wave here will be propagating to the right. And if we know that if the period is t, if we know that the period is t, then if the time is equal to t, that means the time that has passed is equal to the period of the wave. So that means this wave over here would have traveled a distance of the wavelength. Okay, because period is the time taken to complete one complete wave cycle, right? So if the time that has passed is equal to the period, then you know that the distance traveled will be equivalent to one wavelength. So you should be able to see that this wave here will be moving to the right, and you will also see that this point here will go towards this point. So that means you can think that this whole wave cycle here will be move inside the y-axis graph right now. Okay, this whole one complete wave cycle will move into the y-axis graph. So let's see. So when time is equals to period. So this is time equals to 0. As we start our timer, then the graph will move to the right. When t equals to the period, then you will see the wave looks like this. So you see that you have extended by another one complete wave cycle, because one complete wave cycle have already moved it. Okay, this is what happened if time that has passed is equals to the period. But now the question is not asking for period. The question is asking for if t is equals to period divided by 4. If 1/4 of a period has passed, what will happen is the distance traveled by the wave will be lambda divided by 4. Because if you take the amount of, if the time taken is period for you to complete one whole complete wave cycle, then if the time has passed is period divided by 4, then the distance traveled you also get shrink down by 1/4. Okay, so what you should expect is, instead of one whole complete wavelength entering the y-axis graph, you should expect only 1/4 of it. So this is one complete wave cycle. So divide by 2, you get half. So divide by 2 again, you get 1/4. So you should expect only this portion from here to here will be entering the y-axis graph. The rest will still remain outside. We will still remain to the left of the origin. Only this part of the wave cycle will be entering the y-axis graph. So let's see. So this is time equals 0. This is time equals to period divided by 4. So you will see that the graph has shifted by 1/4 of a complete wave cycle to the right. So this will be the new shape of the displacement distance graph. So let's check which one has this shape over here. Well, it starts from the bottom. So definitely not this one. This one starts from 0. This one starts from 0. This one starts from above. This one starts from below. So this one will be our answer. Okay. So yeah, so that's how we solve this question. You have to imagine the situation. If they say time pass is period, then you move by one complete wavelength to the correct direction. If it's time divided by 6, if it's period divided by 6, then you move by 1/6 of a wave cycle. If the time is period divided by 2, then you move by half of the wave cycle. So that's how you think about this kind of question. So that's all for the section on properties of wave. So later we'll be moving on to another video where we'll be discussing questions related to sound intensity.